Now, because we want to move from one city, visit every single city, and then return to the original city, we have n steps total. So we have n cities. We're trying to visit all of them and get back to the original city. So that means we have n steps that we're going to end up taking. And we just said with each step, we are doubling the number of possible paths. So that means the total number of paths that we are going to consider is 2 to the nth power. And that means our algorithm is going to take theta of 2 to the power n time. And this type of algorithm is a little bit different than what we've seen before. Before we've seen our theta notation or our order of magnitude notation be n and then maybe to some polynomial, or maybe it's just n or log n, but here n is an exponent for the power of 2. So this type of algorithm is what we call an exponential algorithm. Now I'm just going to stay up front. Exponential time algorithms are bad. Okay? If you have an exponential time algorithm, it is horrible. It's not going to do any good. It's a waste of time. Don't even bother it. So why is this the case? Well, let's just do some comparisons. Let's compare theta of log n, theta n squared, and theta 2 power n, and let's just see how bad the theta 2 power n time really is. To do that, we're going to fill out this table here with different sizes of n and just see what happens with these different running times. So we'll take a look at when n is 10, 50, 100, and 1,000. Let's take a look at what happens with theta log n as we increase the value of n. So when n is 10, theta log n is going to be 0.0003 seconds. When n is 50, it's going to be 0.0006 seconds. When n is 100, it's going to be 0.0007 seconds. And then when n is 1,000, it's going to be about 0.001 seconds. So no real issues at all. This is really fast. Log n is really good. Now let's take a look at theta of n. So when n is 10, this is going to be about 0.001 seconds. When n is 50, it's going to be about 0.005 seconds. When n is 100, it should be about 0.01 seconds. And then when n is 1,000, it should be about 0.01 second. So once again, it's a bit slower than log n, but it's still really fast when you consider 0.1 second for n is 1,000. That's still really, really good in this case. Now let's take a look at theta of n squared. So when n is 10, we would get 0.1 second, which is still okay. When n is 50, we would get 0.25 seconds. When n is 100, we should expect about 1 second for it. And then when n is 1,000, we would get about 1.67 minutes. So we compared theta of n and theta of n squared before, and we knew that n squared was going to grow faster than n. So at some point, it's going to become much larger than n. So there is a big difference between 0.1 second and 1.67 minutes, but that's still manageable. So an n squared time algorithm, depending on the problem that we're trying to solve, is still okay. Now, like I said before, though, with searching, n squared is bad. Or even searching and sorting n squared is really bad. But in some cases, it is okay. So this is still acceptable as far as how long it takes to solve a problem of size n. Now let's take a look at theta of 2 power n. So when n is 10, it's going to take 0.1024 seconds. Okay, that's not so bad. Now, when n is 50, it's going to take 3,570 years. That is not an exaggeration. Okay, just that one jump from n being from 10 to 50 takes that long in order to solve the problem. And then it gets worse when we increase n even more. When n is 100, it's going to take 4 times 10 to the 16th power centuries. So no one's going to be around long enough to solve that. And then when n is 1,000, just don't bother even trying. That number is way too high to compute. We don't even want to try it. It just takes way too long. So what we're saying here is 2 power n, it grows way too fast when n increases, and there's just no way that we can do this. So like with our Hamilton circuit problem, to say that we'll check all possible paths for a very small n, we can probably do it, But for a large n, even something as 1,000, it is completely infeasible. There is no possible way that we can look at every single possible path. It just takes way too long to solve. So a question we may want to ask is, are there problems where there is no polynomial bounded algorithm for it? And such problems where they don't exist, where these polynomial bounded algorithms exist, are called intractable problems. Now, they are solvable, don't get me wrong, they can be solved, there is a solution for it, but they require so much work, and so these algorithms are just useless. So here they usually involve looking at all possible combinations, which is a solution. It will give us the correct answer. It's just it requires so much work and so much time that it's not a realistic approach. So like here for the Hamilton circuit problem, we suspect that it is an intractable problem. Now I say that we suspect because, well, no one has found a polynomial bounded solution for this problem, and at the same time, no one has proved that such an algorithm doesn't exist either. So I mean, there's this whole field in computer science where we're trying to determine whether or not there are such solutions for problems. There's a whole classification of problems where right now it seems like the only solutions involve looking at all possible combinations. So there's a whole class of problems that we suspect are intractable, but there has not been any formal proofs, no findings of showing about whether algorithms that are more efficient exist or whether there just is no efficient solution for these types of problems. The last thing we'll talk about is just kind of more of a small note. We're not going to go into any details about it, but it is worth mentioning that for some suspected intractable problems, there are efficient solutions for it, but the result that we get is not an exact solution. So we said before that algorithms need to be correct. These algorithms are not correct. Okay, I want to make this very clear. I'm talking about algorithms that are efficient, but they're not correct. They do not give an exact solution. But instead, we get a close approximation, and that, I mean, it's a close enough solution for the problem. And these types of problems, or I should say these types of algorithms, can be done in polynomial time. So what I'm saying here is we have an algorithm that's efficient, it's in polynomial time, and it gives us a solution that is close to the exact solution, but it's not the exact solution. It's a very close approximation. And these types of algorithms are called approximation algorithms. And we're not going to really talk any more about that in this course, but it is worth noting that there are approximation algorithms for some of these suspected intractable problems.